At this point in Chapter 10, we've learned that we can replace an elementary function with an approximating polynomial function. For example, if we take the function y equals sine of x, we can approximate this with a linear function, and that is the tangent line, on a very small interval about the center of our approximation. In this case, the picture I'm drawing here is centered at 0. However, as we move away from 0, the line and the elementary function are very distinct and different. So that linear function, or the tangent line, only approximates sine of x on a small interval. If we want to get a better approximation over a longer interval, we might consider increasing the degree of the polynomial that we're using to approximate the elementary function. So if we use a quadratic function, we may be able to resemble sine of x over a larger interval about x equals 0. Or even better than that, maybe we could choose a third degree polynomial function. As we increase the degree of our approximating polynomial function, you can see that we can more accurately represent the elementary function over a larger interval. So it stands to reason that if I could generate an infinite degree polynomial, then the polynomial and the elementary function would be indistinguishable across a large domain. So at this point, we're going to make the jump from Taylor and Maclaurin polynomials, of finite degree that is, to Taylor and Maclaurin series. So we're dealing with power series, and these are simply going to look like polynomial functions of infinite degree. Here's the definition. Suppose the function f of x has derivatives of all orders on an interval centered at the point C. The Taylor series for f of x centered at C is f of c plus f prime of c times x minus c plus f double prime of c divided by 2 factorial times x minus c squared, continuing this pattern. You can see here, this is fitting the same formula for a Taylor polynomial. What makes this definition different is this ellipsis right here. It shows that this pattern continues indefinitely. If we write this with summation notation, we end up with the sum from k equals 0 to infinity. So we're dealing with an infinite power series. Now, just a reminder, as all this information is still new, a power series contains a variable x, whereas an ordinary series is simply built upon the index either n or k. So when we have a variable as part of our series, it's called a power series. So in this expression, you see the explicit formula for each term of the series over here. I want to point out a couple of things. First of all, derivatives of all orders are involved. Be very careful that when you're expressing a derivative with a number, that you put that number in parentheses. That distinguishes a derivative from an exponent. Also, we have k factorial in the denominator, and notice this series begins counting with the index k equals 0. Now, you may not be familiar with this result, but 0 factorial is actually equal to 1. You can test it out on your calculator. And one little correction here, our series is centered at C. So that's simply a horizontal shift of a polynomial function. So this is the concise representation of a polynomial of infinite degree with real number coefficients. Just a reminder, a Taylor series centered at 0 is called a Maclaurin series. So we're simply making the jump from Taylor and Maclaurin finite degree polynomials to Taylor and Maclaurin infinite degree polynomials. So to generate these series, it helps to start by establishing a pattern with a finite degree polynomial, and that's what we're going to look at on the next few examples. Example 5, consider the function f of x equals cosine of x. Find the first 4 non-zero terms of the Maclaurin series. Then express the series using summation notation. So we're going to work our way up to our infinite series using induction. That is, we're going to look at what's the pattern of the first few terms in that series, and then based on that pattern, we'll be able to write the formula for the explicit term and express the entire infinite degree polynomial in summation notation. So let's get started on this problem. Our elementary function is f of x equals cosine of x. We want to find the first 4 non-zero terms. Now, at first glance, it looks like we're just going to have to find 3 derivatives to get our first 4 non-zero terms. But this one actually turns out a little bit interesting. Now, also notice we're finding a Maclaurin series. That's simply a Taylor series centered at 0, so it's the easier case. So we need to find all of our coefficients. We need derivatives, and we need to evaluate those derivatives at c equals 0. So the given function is f of x equals cosine of x. While we're at it, let's go ahead and evaluate this function at 0. Cosine of 0 is equal to 1. So the first term in our Maclaurin series here is going to be 1. To get the next term, we're going to need the first derivative. So f prime of x, the derivative of cosine of x, is negative sine of x. But notice when we evaluate f prime of 0 or sine of 0, we get 0. If the coefficient of this term is 0, then that entire term will be lost. So this does not qualify as a non-zero term. Let's go ahead and move on to the next one. F double prime of x, the derivative of negative sine of x, is negative cosine of x. When we evaluate f double prime of 0, or negative cosine of 0, we obtain negative 1. That is a non-zero coefficient, and that's going to generate this term. We're looking for the first 4 non-zero terms, so let's continue finding and evaluating derivatives until we've established those coefficients. Next, f triple prime of x, the derivative of negative cosine of x, is going to be sine of x. And f triple prime of 0 is sine of 0 or 0. Now, just like the derivatives of sine and cosine are cyclic, they're either going to be a sine function or a cosine function, and their evaluation, and by the way, they alternate in sign, then their evaluation will also be cyclic. So we see this pattern, 1, 0, negative 1, 0. We're going to see it cycling as we continue finding derivatives. Now, for the fourth derivative, I'm going to express it as the derivative of f with a 4 in parentheses. The derivative of sine of x is cosine of x. And the fourth derivative, evaluated at 0, is cosine of 0. We're back to start this cycle over. We get 1. That gives us 3 non-zero terms. We're looking for 4. I'm thinking we're going to need a couple more derivatives to figure it out. As you can probably anticipate from the pattern, when we evaluate the fifth derivative at 0, once again, we obtain 0. One more derivative will give us 4 non-zero terms. So here we are up to the 6th derivative. The derivative of negative sine of x is negative cosine of x. And when we evaluate it, negative cosine of 0 gives us the anticipated fulfillment of this pattern, negative 1. Now, just out of curiosity, have you ever had to find the 6th derivative before? Did you ever wonder, why would I ever want to find a 6th or a 10th derivative, something like that? Well, a great application of those higher order derivatives is right here in Taylor and Maclaurin series. Now we're ready to assimilate the first 4 non-zero terms of our Maclaurin series. Now I'm going to keep up with our index or our counter here for these terms to keep our information organized. This is going to be our 0th term, first term, second term, third term, fourth, 5th, and 6th terms. Notice that all of our odd terms are zeroing out. They're going to all have a coefficient of 0. So we're just going to be generating the even terms of our Maclaurin series. So the first one is evaluated as f of 0. So the formula is going to look like f of 0 plus, now again, we know that the second term, k equals 1, that one's going to disappear with a coefficient of 0. So our next term is going to look like f double prime of 0 divided by 2 factorial times x minus 0, let's just call it plain old x here, squared. The term for k equals 3 has a 0 coefficient, so now we're looking at the term for k equals 4. So establishing our pattern here, this is going to be the fourth derivative evaluated at 0 divided by 4 factorial times x to the fourth. We need one more non-zero term. K equals 5 has a 0 coefficient. K equals 6 has substance. So this will be the sixth derivative evaluated at 0 divided by 6 factorial x to the sixth. Plugging in our details here, f of 0 is 1. F prime of 0 was negative 1. So let's write it negative 1 over 2 factorial. 2 times 1, 2 factorial is 2x squared. The fourth derivative evaluated at 0 is positive 1. 4 factorial is 4 times 3 times 2 times 1. That gives us 24, x to the fourth. And finally, the sixth derivative of f evaluated at 0 is negative 1. 6 factorial turns out to be 720. Remember, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So that gives us 720 times x to the sixth power. So the first 4 non-zero terms of our Maclaurin series are these 4 terms. What we want to do next is make the jump from 4 terms to an infinite number of terms. That is, we want to say, what does the entire Maclaurin series look like? Now, I don't know about you, but I don't have enough time to write down an infinite number of terms, so we better do it with summation notation so we can do it in a finite amount of time, right? So we need to express this in terms of a explicit formula. We'll start with k equals 0, so this will be the 0th term. This will be our first, second, third term. Now, notice in the denominator, we've got a factorial. In the numerator, we have either a positive 1 or a negative 1, and then we always have an even power of x. So let's begin by programming in the alternating sign. We can write this as negative 1 to the kth power. Now pause for just a minute. If we raise negative 1 to the 0th power, for our first term, we're going to get a positive number. If we let k equal 1 for our first term, we get negative 1 to the first power, which is a negative number. So it looks like we have the pattern of alternation correctly programmed into our explicit formula here. The next thing we can observe is that we have a 1 in the numerator of every single one of those fractions, or no other substance. And in the denominator, we have a factorial. Now, for k equals 1, we had 2 factorial. For k equals 2, we had 4 factorial. For k equals 3, we got 6 factorial. So we're just simply multiplying that k by 2 to make it an even number, right? If k is an integer, 2k is an even integer, and then finding the factorial of that. In addition, we have a power of x, which is an even power of x, so we can program that in with a 2k in the exponent. So this represents the polynomial of infinite degree that resembles this elementary function f of x equals cosine of x. Remember, if you have a polynomial of infinite degree, it's going to be twisting and turning, crossing the x-axis, hitting those maximums and minimums, and you have the potential of an infinite number of zeros, so you can see how that would begin to resemble a cosine wave. So on this problem, we started with the formula for a Taylor series. We recognized that it was a Maclaurin series, so we plugged in c equals 0. We found the value of the function and its derivatives. We've generated enough terms until we could get non-zero coefficients. And we used this formula to generate the first 4 terms of that Maclaurin series. From the nature of those terms, we were able to recognize the pattern of the series and express it as an infinite degree polynomial, or more technically, a Maclaurin series. So we're going to do the similar type of process on example 6. Consider the function f of x equals e to the negative x. Find the first 4 non-zero terms of the Taylor series centered at c equals natural log of 3. Once we get those first 4 terms, we're going to induce the pattern for the general series, or that is the series to infinity. So we need to begin by evaluating our function at the given center. So our function is e to the negative x, and this is a Taylor series, so we're not evaluating these functions at 0. In this case, we're evaluating them at natural log of 3. So we need to evaluate e to the natural log of 3. Now, using properties of logarithms, we could move that -1 coefficient to the exponent of the argument, and then we can see by inverse property here, e to the natural log of something is that something. So the result of this is 3 to the -1, and I prefer to write it as 1/3. So our first coefficient will be 1/3. The second coefficient comes from f prime of x. That would be -e to the -x. Then we're going to evaluate f prime at natural log of 3. That's going to be -e to the natural log of 3. Now, we don't need to go through all the steps again. We saw from the previous line that e to the natural log of 3 simplifies to 1/3. So we can assume -e to the natural log of 3 will simplify to -1/3. That'll be our next coefficient. Then f double prime of x, we're back to e to the -x. And f double prime of natural log of 3 is e to the natural log of 3, or +1/3. Just like the derivatives of sine and cosine are cyclic, we're seeing the same thing going on with our exponential function. So by generating the first few terms of our Taylor series, we're able to see the pattern and induce the formula for the infinite Taylor series, infinite degree polynomial. All right, we have our coefficients. Let's go ahead and begin developing this Taylor series. Now, according to the formula for the Taylor series, we begin with f of c, then we have f prime of c times x minus c to the first power, f double prime of c divided by 2 factorial times x minus c squared plus f triple prime of c divided by 3 factorial times x minus c cubed. That will give us the first 4 terms. We needed fewer derivatives on this problem because, again, on the previous problem, we had so many 0 coefficients popping up. So f of c, which in this case is natural log of 3, generated the value 1/3. F prime of c is -1/3, and x minus c would be x minus natural log of 3. Next, f double prime of c was +1/3. We have a 2 factorial in the denominator. I'm just going to express that as 2. X minus c is x minus natural log of 3, and we square that. Finally, f triple prime of natural log of 3, we ended up with -1/3. We have 1/3 factorial, which reduces to 6, and we have x minus natural log of 3 raised to the 3rd power. So that gives us the first 4 non-zero terms of our Taylor series. I think I will take one step here to simplify the coefficients. We'll call this one a 1/6 coefficient, and we'll call this one 1/18. And those are the first 4 terms of our Taylor series approximating e to the -x centered at natural log of 3. Now we want to jump from 4 terms to an infinite number of terms. We're going to express this as the sum from k equals 0 to infinity. Now, when I generate this series, I'm going to go back and actually look at this step before I simplified. I can see more details of the pattern there before I simplified those coefficients. I notice every single term has a 1/3 coefficient. So what I want to do is factor that out, and in fact, we can put it in front of our summation sign and simplify our explicit formula a bit. Also notice, as we go from term to term, let's call this k equals 0, k equals 1, k equals 2, k equals 3, we see that the sign once again alternates. So we will program this in to our explicit formula as -1 to a power. Now, double checking, when k is equal to 0, -1 to the k is a positive term. So our first term is positive, that works out. And when k equals 1, -1 to the first power is negative. So it looks like we got our signs in the right order. If they were reversed, by the way, we could correct that by saying k plus 1, okay? But ours was originally correct. Also, we can recognize from the formula before we simplified it that we did have these factorials in the denominator. So we're going to have a k factorial in the denominator. And then we have our variable term x minus natural log of 3 to the k power. So there is the infinite degree polynomial, or our Taylor series, which approximates this exponential function centered at natural log of 3. So if we were able to graph both of those functions, they would be indistinguishable over a very large interval. So in this section, we made the jump from looking at finite degree Taylor and Maclaurin polynomials to jumping into Taylor and Maclaurin series, which you can think of as infinite degree polynomials. In the next video, we'll look at what's the purpose of this. Why would you want to replace an elementary function with an infinite degree polynomial?